We've been through the darkness, where the only light was from the fires that burned our souls. We journeyed, until finally we were able to crawl out of the gates of hell. Now we're here, due to our knowledge of AP Chem.
AP Chem? Who's that?
Spencer, we were down there for a year.
Okay, Spencer, let's start with something simple, like electrochem.
Electrochem? What's that?
Cue the intro. So Spencer, you remember what this is?
Isn't it called a Botox reaction?
No, that's a redox reaction. In this, one thing's reduced and another is oxidized. And in this case, the zinc is oxidized and the copper is reduced.
In the redox reactions that we're used to, you see a solid in a solution, in this case a zinc solid in a copper sulfate solution. What you don't really get to see is the electrons jumping from one to the next. And all we really get to see is the copper precipitate at the end.
In this case, the zinc and copper are separated, and you can see the electrons moving from the zinc through the copper solid into the copper solution. Zinc 2 plus comes off of the zinc, and the electrons combine with the copper 2 plus in the solution.
Hey Luke, don't forget, zinc deteriorates as more solid copper is produced, and this leaves Zn2 plus and sulfate left from the standing solution.
Spencer, we didn't know you knew that.
Dude, I told you I'm good at trigonometry.
This isn't trigonometry.
As you can see here, we have a galvanic cell, which we still have the zinc on the left and the copper on the right in their solutions. And when you have this set up, you get current passing through. You get electrons passing through the wire, which you can measure using a voltmeter.
Yeah, so here we have a voltmeter. I know a lot of you probably don't think you've got one in your house, but we're just here to show you that you really do. And how it works, you just put the battery in, and like that. You get the cover on, make sure it's locked on there, and see it's on. It's working, so this one takes about 5 volts, so you can see actually what it is. And yeah, whenever you're working on a project, sometimes it's good to just take a break. So yeah.
Luke, aren't you supposed to be working on your project? Come on,
Mom, get out! Mom,
Luke,
stop!
Luke, get back to work.
Another part of the galvanic cell that we have to talk about is the salt bridge. The salt bridge's main purpose is to keep both solutions neutral. This is important because if the solutions weren't neutral, that would be a result of the anode deteriorating, which would mean Zn plus being added to the solution. And if the Zn plus doesn't have anything to bond to, then it's going to pull back on the electron and prevent current flow. It accomplishes this by being comprised of KCl. And KCl is a soluble molecule, which means it can dissolve in the solutions. So this allows Cl minus to be able to bond to the Zn2 plus, and K plus being able to bond to the SO42 minus.
Another important aspect to the galvanic cell are the electrodes, one of which is the anode. And at the anode, oxidation takes place. You can tell that there's oxidation at the anode because they both start with vowels. And another thing to remember this is Lioger. So loss of electrons is oxidation. And with the O, it means oxidation, which leaves the cathode for being reduced. And you can know this from the second part of Lioger, which is gain electrons is reduction.
Standard cell potential is a measure of the strength in volts that drives the chemical reaction at standard condition. In this equation, you see that the potential of the cell is equal to the production potential of the cathode and anode according to Yahoo Answers. This is a table of standard reduction potential. Here, zinc and copper is circled, and if you plug them into the equation, you get a standard cell potential of 0.91 volts.
As you can see, this galvanic cell actually looks a little bit different than the normal galvanic cell. It has the same metal and solutions at both the anode and the cathode. The only difference between the electrodes are the concentrations of the solutions. When you have this setup of a galvanic cell, it's called a concentration cell. Now, the concentration of the solution at the anode is actually smaller than the concentration of the solution at the cathode. If they were the same, everything would already be at equilibrium and no charge would be shown in the voltmeter. But since the concentration of the solution at the anode is smaller, an equilibrium must be reached, so a very small charge has to be shown in the voltmeter.
Here we have another galvanic cell that looks a little bit different. Actually, it's not a galvanic cell. Tricked ya! This is an electrolytic cell. And electrolytic cells are basically the opposite of galvanic cells, in the sense that instead of producing an electric charge, they need an electric charge in order for them to work. So if we just stick a battery right in there, we can see that electrons coming from the negative side of the battery combine with Na plus in the solution formed from the NaCl dissolving in the solution and combine to form Na solid at the cathode. Now at the anode, we see 2Cl minus, again from the NaCl dissolving, releasing 2 electrons towards the positive side of the battery, and then forming Cl2 at the anode.
Hey Spencer, do you finally understand electrochemistry?
Yeah, dude, I think I got it. I think I can pass the test. Now, I can make my own battery. Day 87. It's been about 5 months since I started working on this terrible battery. It's consumed so much of my life. All my friends and family, they've left me because I spend so much time working on this battery. It looks so much easier on YouTube.